So imagine this. You've just downloaded a new app, right? Maybe it's a new productivity tool or a banking interface.
Right, something you're going to use every day.
Exactly. And visually, it looks absolutely stunning. I mean, the colors are beautiful. The typography is super modern. They've got these custom illustrations.
But then you try to actually use it.
Yeah. The second you start tapping around, something just feels, I don't know, off. You can't quite put your finger on it. You're accidentally tapping the wrong buttons. Your eyes get tired reading the onboarding screens. And there's just this like lingering low-level anxiety.
Oh, that is so common. It's the uncanny valley of user interface design.
Yes, it's the digital equivalent of like walking into a room where every single piece of furniture is angled just 2 degrees to the left.
Which is actually a documented psychological response, believe it or not.
Wait, really? There's a term for that.
Oh, yeah. We call it cognitive friction.
Cognitive friction. Okay, I like that.
Yeah, and it usually happens because the designer, they treated the screen like a blank canvas to paint on, rather than an architectural space that needs to be engineered.
Ah, I see. So they're just placing things where they look pretty.
Exactly. But the human brain is a pattern recognition machine. So when it enters a new environment, whether that's physical or digital, it immediately starts mapping the geometry of that space.
It's looking for the rules.
Yes, it's looking for structural rules. And when it finds a set of mathematical rules, the brain can actually relax.
Right, because it stops actively processing the layout and just focuses on the actual content.
Exactly. But when those rules are absent, or, even worse, if they're inconsistent, the brain has to work overtime just to figure out where to look next.
Which causes that low-level anxiety we were talking about.
Spot on.
Well, decoding that invisible geometry is exactly what we are doing today. We are going to explore the underlying mathematics that, frankly, separate amateur interfaces from world-class digital products.
It's a huge shift in perspective.
It really is. And to do this, we are pulling our entire analytical framework from a truly phenomenal resource, especially for anyone just starting to build out their design career.
Oh, absolutely. It's foundational stuff.
We're looking at Chapter 08, which is titled Layout and Grid, from the book Design User Interface. It is practically a masterclass in structural layout.
It's so good. It really fundamentally shifts how you look at a screen.
We are going to tear it right down to the studs. Because once you grasp this, you stop seeing buttons and text fields, right?
Yeah, you start seeing the actual matrix of invisible constraints that govern them.
So here's the roadmap for this deep dive. We're going to explore why establishing this grid has to be your very first priority. The define ASAP principle.
Crucial step.
Then we'll dissect the algorithmic logic behind fluid versus fixed spacing, break down a highly specific real-world component called the matrix, and finally pull out some golden good practices.
The stuff senior designers use to actually bridge the gap between Figma and functional code.
Exactly. So let's start at ground zero, the blueprint. What is a grid, really?
So, a grid is basically, at its core, a system of intersecting lines. It creates a framework for organizing content.
But it's more than just a tool for lining things up.
Or much more. Treating it just as a way to align elements is missing the broader point entirely. A grid is really a system of proportion.
Okay, proportion.
Yeah, it dictates the hierarchy of the screen. Think about like classical architecture.
Okay, like the Parthenon or something.
Perfect example. The Parthenon wasn't built by just, placing pillars wherever they look nice to the architect.
Right, put one here, put one there.
Exactly. It was built on rigid mathematical proportions. And digital design requires that exact same level of foundational integrity.
What's fascinating to me, though, is that the user never actually sees this Parthenon.
No, never.
They never see the pillars. The structural blueprint we are talking about is completely invisible in the final compiled software.
Yeah, the grid lines disappear.
I often think about it like the skeletal structure of the human body. You don't look at someone and see their skeleton.
Right, that would be terrifying.
Yeah, a bit creepy. But their skeleton dictates their posture. It dictates how their clothes hang, how they move through physical space.
That's a really great analogy.
And if a femur is, say, an inch shorter than the other one, the entire system has to compensate. The person limps.
And in UI, a deviation of just 3 or 4 pixels from the underlying grid creates a visual limp.
A visual limp. I love that. And if the user can't actually see those lines, why does a subtle deviation of just a few pixels have such a massive impact?
Because that visual link scales horribly. So if you can misalign one element by 3 pixels, right?
Okay.
And then the next element aligns to that first one, the error compounds.
Oh, man. So it just gets worse and worse.
Exactly. By the time you scroll down to the bottom of the screen, the entire interface looks like it's structurally collapsing.
Which goes right back to that cognitive friction.
Yep. And this is why the methodology we're discussing stresses one overarching imperative. You have to define the grid as soon as professionally possible.
Define ASAP.
ASP. It is the very first structural decision you have to make.
Because if you delay that decision, you aren't just creating a mess in your design file. You are creating an absolute nightmare for the engineering team.
Oh, the developers will hate you.
Right, because developers don't build software by manually placing elements with some arbitrary pixel count.
No, they build using global variables and cascading logic.
So if your design has a consistent grid, a developer can just write a single class in their CSS or their React code.
Yeah, and that one class governs the spacing for the entire application. They define a container, set the gap property to a standard variable, and bam, the layout essentially builds itself.
But if the designer's just eyeballing it...
Oh, if they're eyeballing it, it's a disaster. Yeah. Like if there's a 14-pixel gap here, an 18-pixel gap there, a 15-pixel gap on the next page.
The developer has to write custom, hard-coded exceptions for every single element.
Exactly. And that is exactly how you bloat a code base. You're introducing massive technical debt before the product is even launched.
It slows deployment to an absolute crawl.
Completely.
But here is where Chapter 08 introduces a really compelling tension. Because it screams, define the grid ASAP, right?
Yeah.
But in the exact same breath, the book warns against locking in an arbitrary grid on day one before you actually understand the product.
Right. You can't just pick a 12-column grid blindly and hope it works. It demands a pre-flight testing phase.
A pre-flight phase.
Yeah.
So explain that. How do we test it?
Well, a grid is only as good as the content it can hold, right? So if you lock down a highly restrictive, rigid grid structure before you know what kind of data the application actually has to display.
You're going to design yourself into a corner.
Exactly. You have to stress test the structure first.
I really love this concept of stress testing a layout. The approach requires you to take your absolute worst case scenario and your absolute best case scenario, and then you force them to coexist.
Yeah, you have to make sure the same grid handles both extremes.
So let's say you are designing this massive enterprise SaaS product.
Okay, a big SaaS dashboard.
The worst case scenario is usually a heavy, incredibly dense data dashboard. We are talking intricate financial charts, massive multi-column data tables with sorting arrows.
Tiny status indicators everywhere.
Right, complex filtering menus. It's just an overwhelming amount of information that needs to be digested all at once.
And that kind of density requires immense granularity.
So a basic grid won't work.
No, a basic 4-column or even an 8-column grid simply won't give you enough tracks to align all those microelements. You need more lines.
Right, but then inside that exact same application, you might have a simple settings page or like a full screen text article in the help center.
And that is your best case scenario.
Exactly. It's just a single wide column of clean text. So if you choose a grid that is so complex that it easily handles the data table, it might make the simple text article look fragmented.
Yeah, and if you choose a grid that's perfect for the article, the data table is going to completely break the container.
So what's the solution?
This is why the methodology recommends scaling up the complexity of your columns based on the density of the product.
Okay, scaling up.
Yeah. For these highly complex, multifaceted projects, moving up to a 16-column grid is often the safest bet.
16 columns, that sounds like a lot.
It does, but 16 is actually a brilliant number because of its modularity.
How so?
Well, you can span a hero image across all 16 columns. Or you can drop in 4 cards that take up 4 columns each.
Oh, right, or an 8 and an 8.
Exactly. You can have a sidebar that takes 3 columns, leaving 13 for the main content. It gives you maximum flexibility to handle that crazy dashboard.
While still providing a clean mathematical container for the simple text block.
Exactly.
Okay, so we've run our pre-flight checks, we know the extremes of our content, and we are ready to actually build this mathematical skeleton.
The fun part.
Yeah.
Yeah.
Which brings us to the anatomy of the grid itself, and we really have to address the terminology straight away because it is notoriously confusing for anyone stepping into system design.
Oh, the naming conventions are terrible.
They really are. We talk about the horizontal grid, but the horizontal grid is constructed entirely of vertical lines.
It is the ultimate paradox in design nomenclature.
It sounds completely backward. Like, why on earth is it called horizontal if the lines go up and down?
Because of how we use it.
Right.
The name doesn't come from the physical lines you draw. It derives from the axis of movement it controls.
Ah, right. So we use it to align elements side by side, horizontally across the screen.
Precisely. You're establishing the x-axis rhythm.
Got it. And this horizontal structure is built from two primary ingredients. First, you have the columns.
Yep, those are the actual active tracks where your content lives. Your images, your text blocks, your buttons, they all sit inside these columns.
And the second ingredient is the space between those columns, which we call the gutters.
The gutters, yeah.
I used to think of gutters as just empty, dead space, but they are actually the most active structural element on the page.
Oh, they do all the heavy lifting.
I like to think of the grid not as a flat drawing, but as a physical Lego base plate.
Okay, a Lego bus plate.
Yeah, so the gutters are the physical pegs sticking up from the board. They are rigid. They force the columns into specific mathematical increments.
Because you can't just slide a column halfway into a gutter.
Exactly. Just like you can't snap a Lego brick halfway between two pegs. It doesn't fit. The gutters enforce the discipline.
I really like that analogy. That physical constraint is what guarantees alignment. But, if the horizontal grid controls the x-axis, we really have to look at the other half of the equation.
The one that always gets neglected.
Yes. The vertical grid, or, as it's more commonly referred to in typographic circles, the vertical rhythm.
Because it controls the y-axis. It governs how elements flow vertically down the page.
And this one is built using horizontal lines, naturally.
Naturally. And while a lot of designers will just obsess over their 12-column horizontal grid, they completely ignore the vertical rhythm.
They'll just nudge elements up or down until it, looks right.
Yeah, looks good enough. But why is standardizing the vertical heights and the white space between sections so critical? Why should we care?
It fundamentally comes down to how human beings consume digital content. We do not read web pages like we read a book.
Right, we scan them.
Exactly. Our eyes travel down the screen in rapid jumping movements. They're called saccades.
Saccades.
Yeah. And the brain is constantly looking for visual anchors to understand where one thought ends and another begins.
Okay, so the vertical grid establishes a predictable cadence for those anchors.
It sets the tempo of the scroll.
The tempo of the scroll, that's a great way to put it.
Think about it like this. If the white space between your heading and your paragraph is 16 pixels, and then the space between that paragraph and the next section is 64 pixels.
The brain registers that big 64-pixel gap as a major shift.
Exactly. It understands without reading a single word that a new topic is beginning.
But if you ignore vertical rhythm...
Yeah, if you make one gap 40 pixels, the next 55, the next 20, the cadence is broken.
The user has to manually evaluate every single block of text just to understand its relationship to the others.
Which creates massive reading fatigue.
And Chapter 08 explicitly points out that when you combine a strict horizontal grid with a mathematical vertical rhythm,
when you align objects to both the X and Y axis simultaneously,
something magical happens. The layout stops feeling like a collection of floating objects. It locks into what feels like a solid, unmoving matrix.
Because the eye never has to guess where the next piece of information will land.
It is always exactly where the geometry predicts it will be. It's effortless to process.
But, of course, maintaining that perfect geometry introduces the biggest challenge in modern UI architecture.
Right, because screens aren't just one size anymore.
That perfect X and Y matrix is relatively easy to maintain if your canvas never changes size.
Which is never the case.
Exactly. A single application might be opened on a 32-inch ultra-wide desktop monitor, a 13-inch laptop, an iPad in portrait mode, and a tiny budget smartphone.
The canvas is infinitely variable.
Which kicks off the battle of the layouts.
Yes. How does the grid respond to a screen that refuses to stay the same size?
Well, the book outlines two primary philosophies for dealing with this: the fixed grid and the fluid grid.
Let's start with the fixed approach, because it is highly controversial, especially for people outside of the design world.
Very controversial.
A fixed grid is completely rigid. It relies on a set, mathematically absolute value for the columns and the gutters.
They do not stretch. They do not shrink.
Right. If a column is 60 pixels wide, it stays 60 pixels wide forever.
And the immediate consequence of that rigidity is what happens when the screen is larger than the grid itself.
Okay, so if your fixed grid is, say, 1,100 pixels wide in total?
Yeah, and a user views it on a 4K monitor that is 3,800 pixels wide, the grid just sits dead center.
And you are left with massive oceans of completely blank space on the left and right sides of the content.
And this is exactly where clients and stakeholders usually panic.
Oh, I've been in those meetings. They look at a massive monitor and say, we have all this expensive screen real estate. Why are we leaving it blank?
Stretch the content, make it wider, use the space.
Yeah. It feels highly counterintuitive to leave 60% of your screen totally empty. Isn't that just a waste of screen real estate?
It feels counterintuitive until you understand the biology of human vision.
The biology, okay, explain that.
There is a very specific reason why platforms like Wikipedia or the New York Times or massive blogging portals utilize fixed grids. They usually cap out around 1,200 or 1,400 pixels maximum width.
Because if you take a paragraph of text and stretch it across a 3,800 pixel wide monitor,
You have completely destroyed its readability.
because of the physical distance the eye has to travel, right?
Yes. When you read, your eye tracks along the line from left to right. When it reaches the end, it has to perform what is essentially a physical reset.
It snaps back to the left margin to find the beginning of the next line.
Exactly. And if that line of text is literally 2 feet wide on a massive monitor, that snapback is a massive physical movement.
The eye easily loses its place.
You end up accidentally rereading the same line or skipping 2 lines down. The tracking mechanism of the eye completely breaks down over that distance.
It is physically exhausting. It literally strains your neck and your ocular muscles.
It really does.
So those massive blank spaces on the sides of a website aren't wasted space at all. They are protective barriers.
That's a great way to think of it.
The fixed grid is a container designed specifically to protect the optimum reading length. It forces the content to stay within the biological limits of human comfort, regardless of how massive the hardware gets.
It prioritizes human biology over screen utilization.
Okay, that is a brilliant way to frame it. But while fixed grids are incredible for text-heavy editorial sites, they aren't always the best solution for complex, highly interactive software. Right?
No, not at all. If you're building a SaaS dashboard or a dynamic web app, you need something different.
That is where the fluid grid takes over.
Exactly. The fluid grid fundamentally flips the mechanics of the layout. In a fixed grid, the columns are rigid. In a fluid grid, the columns act like liquid.
I love this concept. Let's explain the algorithm of how a fluid grid actually calculates its spacing, rather than just doing raw arithmetic.
Okay, so in a fluid system, there are elements that are strictly anchored and elements that are entirely flexible.
The anchors are your outer margins, right? The breathing room on the far left and right of the screen.
Yep, outer margins and your gutters. Spaces between the columns. Those are non-negotiable hard numbers.
So if you declare your outer margins to be 32 pixels and your gutters to be 16 pixels,
Those numbers will never, ever change, whether the browser is 1,000 pixels wide or 1,005 pixels wide.
so the margins and gutters act like a rigid glass container with internal dividers, and the total width of the screen is the volume.
Yes, and the columns are simply the water you pour into that container.
You subtract the rigid space of the margins and gutters from the total screen width, and whatever space is left over is distributed evenly to the columns,
They simply expand or contract to fill the void.
which means the actual width of your columns in a fluid grid is rarely a clean, round number.
No, almost never. It might be like 41.3 pixels wide.
And that is perfectly fine, because the column width is merely the mathematical remainder of the equation.
Right. The constant, reliable cadence of the 16-pixel gutters is what holds the visual alignment together, even as the content stretches and squishes like an accordion across random device sizes.
And this brings us to a massive revelation about those numbers we keep throwing around. We keep saying 16 pixels, 32 pixels, 64 pixels.
Yeah, that isn't random.
Not at all.
Yeah.
This brings us to the mathematical heartbeat of this entire framework, the magic of 8, the foundational base value.
Any successful design system starts by defining a base metric. It is the atomic unit from which every single other measurement is multiplied or derived.
And in modern UI architecture, the undisputed industry standard is the 8-point grid system.
It's everywhere.
But why 8? I mean, if we are creating a completely arbitrary mathematical system, why wouldn't we just use 10? The metric system is based on 10. It's incredibly easy to multiply.
We have 10 fingers.
Right. Why did the entire tech industry universally agree to build software based on the number 8?
It's a great question. And it actually has nothing to do with visual aesthetics. It has everything to do with hardware rendering.
Hardware rendering.
Yeah, we have to look at how screens actually draw pixels.
Yeah.
So decades ago, screens had a 1-to-1 pixel ratio. 1 digital pixel equaled 1 physical hardware pixel on the monitor.
Simple enough.
But then, high-density displays were invented. Apple's Retina displays, high-DPI Android screens. Suddenly, a screen wasn't just 1x. It was 1.5x, 2x, 3x, or even 4x pixel density.
Meaning they were packing 4 physical pixels into the space of 1 digital pixel to make the image incredibly sharp.
Exactly. Now imagine you design a box that is 5 pixels wide. and the system needs to scale it up for a 1.5x display.
Okay, 5 multiplied by 1.5 is 7.5.
Right, but you cannot have half a pixel on a screen. A hardware pixel is a physical light bulb. It is either on or off. You can't turn on half a pixel.
Oh, so what does the computer do?
The rendering engine has to guess. It either rounds up to 8 or down to 7, and this causes anti-aliasing, which makes the edge of your box look blurry, fuzzy, and completely unsharp.
And this is where the number 8 becomes practically miraculous.
Exactly. The number 8 and its multiple 16, 24, 32 scale flawlessly across almost every single hardware pixel density currently in existence.
Because 8 divides cleanly and it multiplies cleanly.
Yes. If you build your entire layout on base 8 mathematics, your interface will render with razor-sharp subpixel perfection on a cheap 1x monitor, a 2x Retina laptop, or a 3x flagship smartphone. The math completely eliminates rendering blur.
So you choose 8 as your atomic unit, and from there you build a scale. You can just multiply it by 2. 16, 32, 64, 128.
Which creates a very strict, highly contrasting geometric scale.
But wait, if we are just multiplying by 2, why not just use 16 as the base and save time?
Because the 8-point increment is crucial for tiny, intricate component work. While 16 is great for a massive layout, you need the smaller 8-point increments to perfectly position, say, the text inside a tiny button.
I see. So you can also just add 8 incrementally for flexibility. 8, 16, 24, 32, 40.
Exactly.
Let's actually walk the listener through a specific fluid grid math example from the text to make this concrete.
Let's do it.
Okay, take a 390 pixel widescreen, standard mobile size.
Yep.
We subtract 2 32-point outer margins. That leaves us with 326 pixels.
Okay.
Then we want a 6-column grid, so we need 5 gutters. We subtract 5 16-point gutters. That's 80 pixels.
Leaving 246 pixels.
Exactly. Divide that remaining 246 pixels by 6 columns, and you get exactly a 41-point column width.
It works perfectly. But, this level of strict mathematical scaling introduces the concept that is rapidly taking over modern product design.
Right, the soft grid.
The soft grid. It is really the evolution of everything we've been discussing.
Because we've talked a lot about invisible columns and rigid tracks on a canvas.
But in modern development environments, specifically when coding with CSS Flexbox or building native mobile applications in SwiftUI, forcing content into rigid vertical column tracks is actually quite difficult and often entirely unnecessary.
Because the code doesn't natively think in columns. It thinks in relationships.
Exactly. So the soft grid abandons the concept of rigid column tracks entirely. Instead, it applies the 8-point math strictly to the relationships between objects.
So instead of a fixed cage, a soft grid is simply a universal rule. Every single outer margin, every single padding, every single gap between any two elements on this screen must simply be divisible by 8.
It is the ultimate translation layer between the designer's brain and the developer's code.
So the designer isn't trying to align a button to an invisible vertical line on a 12-column grid?
No, they are just ensuring that the space between the button and the text above it is exactly 24 pixels.
It creates a universal rhythmic cadence without the restrictive cage of a fixed column structure. It's way more natural for designers and significantly easier for developers to actually code.
It allows the interface to breathe dynamically while still maintaining absolute mathematical proportion.
Okay, so we have covered the massive macro-level layout architecture.
The big picture.
Yeah. But a layout is completely useless if the actual objects you place inside it are a cluttered mess. A perfect fluid grid doesn't matter if the elements living inside the columns look chaotic.
True.
So we need to zoom all the way in. We need to look at the microgrid. And Chapter 08 provides a brilliant practical breakdown of a component which is aptly named the matrix.
This is where we really see how the macro rules apply at a microscopic level.
Because a component, whether it's a navigation bar or a user profile card or a checkout button, it has to obey the overarching grid of the page, right?
Yes, but it must also establish its own internal grid rules.
Sure.
It is a microcosm of the entire system.
So the example provided in our source framework is a movie card for the film The Matrix.
Let's vividly paint this picture for everyone listening, because visualizing the spatial relationships is key here.
Okay, imagine a sleek, dark mode rectangular card. At the very top, there is a tiny pill-shaped tag that reads Cyberpunk Sci-Fi. Below that tag is the main title, The Matrix. Underneath the title is a dense paragraph of descriptive text detailing Neo, Morpheus, and the simulation.
The synopsis.
Right. And finally, anchored at the very bottom, is a metadata line, release date, 1999.
Structurally, it is a very standard, text-heavy card component.
Yeah.
It's exactly something you would see on Netflix or Hulu.
But the genius of this specific breakdown is how it leverages the 8-point mathematical scale to organize that dense information visually before the user even reads a single word.
It does this entirely through the rule of proximity.
The rule of proximity, which is one of the most powerful laws in Gestalt psychology, right?
Oh, absolutely.
Yeah.
It states that the human brain will automatically group items together that are placed physically close to one another, assuming they share a relationship.
And we control that proximity using our 8-point scale. In this movie card, we only use 3 distinct measurements to create the entire visual hierarchy, 8, 16, and 32.
Okay, let's break down where those measurements actually go.
Sure, so the main title, the matrix, and the descriptive paragraph below it are intimately related. The title is the subject, the paragraph is the definition.
Because they have a tight conceptual relationship, we give them the tightest physical relationship. We separate them by only 8 points.
And the brain instantly registers. These 2 pieces of text are a single unit of thought.
Exactly. Now, what about that cyberpunk sci-fi tag sitting above the title?
Well, it's related to the movie, obviously, but it is categorical data, not the main narrative. It needs to be visually distinct.
So we bump the spacing up, we separate the tag from the title by 16 points.
That 16-point gap creates a subtle visual breath. It tells the user's subconscious this is related information, but it is a separate category.
And finally, we have the outer boundary. The entire movie card itself needs to be separated from the next movie card beside it in the grid.
Which is a complete break in thought. We are moving from one movie to an entirely different one.
So we use the largest measurement in our scale. We push the cards a full 32 points apart.
8 points for an intimate connection, 16 points for a related grouping, 32 points for a complete separation.
You are engineering the user's reading flow purely through the math of empty space.
It's beautiful.
Yeah.
But there is a hidden trap here, specifically when dealing with typography inside these components.
The bounding box issue.
Yes. You can set your spacing to exactly 16 points in Figma, but when you drop the text onto the canvas, it visually looks misaligned. The spacing looks uneven, even though the math says it's perfect.
This is the invisible variable that destroys so many junior designers' layouts.
Explain typography alignment and the CAP height.
So when you type a word into design software, the software doesn't just draw the letters, it generates an invisible bounding box around the text.
And that bounding box is usually significantly taller than the letters themselves.
Because it has to account for the highest possible ascender in the font family, like the top of a capital A or the tall stem of an H.
Right.
And it also has to account for the lowest possible descender, like the tail of a lowercase y or g.
So even if you type a word with no descenders, like the word matrix in all caps, the bounding box still drops way below the baseline to save room for letters that aren't even there.
Exactly. Which means if you tell the software to put exactly 16 pixels of space between the text box and the edge of the card, you aren't actually getting 16 pixels of visual space.
You are getting 16 pixels plus whatever arbitrary empty padding is built into the font's bounding box.
The math is perfectly accurate, but the optical reality is completely broken.
So how do we fix it?
We strip the bounding box away. We align our mathematical grid directly to the physical anatomy of the letters. The book advises anchoring your spacing to the CAP height.
The CAP height being the literal flat top of the capital letters, or sometimes the X height for lowercase.
Right. You align the top of your padding mathematically to the flat roof of the capital letters, and you align the bottom of your padding strictly to the baseline.
The invisible line that the letters actually sit on.
By ignoring the font's bounding box and anchoring directly to the CAP height and baseline, you force the typography to obey the strict 8-point physics of the component.
It stops floating arbitrarily and locks firmly into the matrix.
That is the exact kind of granular, microscopic detail that takes an interface from feeling okay to feeling razor-sharp and premium. It's all in the math.
All right, we have traversed from the massive philosophy of architectural grids down to the sub-pixel alignment of a single letter. To wrap this up, let's distill this into practical execution. We need the good practices.
The actionable stuff.
Exactly. If someone is listening to this and they are opening a blank canvas right now, what are the golden rules they must apply today?
The single most impactful rule we can extract from this framework is what we can call the golden text rule.
Oh, okay, heavy.
We discussed the biological limits of reading on massive monitors earlier, but this rule gives you the exact formula to prevent eye strain. If you're utilizing a standard 12-column grid, your primary body copy long paragraphs of text should absolutely never exceed 8 columns in width.
Never stretch text wider than 8 out of 12 columns.
Never. And there is a very specific, deeply researched typographic reason for this. An 8-column width, generally speaking, translates to roughly 10 words per line.
10 words per line.
And a century of print and digital typography research has universally proven that 10 words per line is the exact sweet spot for comfortable reading and scanning without eye fatigue.
It is the perfect length that allows the brain to absorb the context of the sentence while keeping the physical travel distance of the eye short enough to effortlessly snap back to the beginning of the next line.
If you stretch it to 10 columns, the user's eye fatigues.
And if you stretch it across all 12 columns, they will literally read the first 2 sentences, get exhausted, and abandon the page entirely.
You are quite literally designing against human biology.
So what's the next vital practice?
It's a plea for structural simplicity. Junior designers often try to prove their creativity by inventing massively complex asymmetrical overlapping grid structures.
Because they think a simple grid is boring.
Right. But the methodology explicitly warns against this. Simplicity wins. Creativity in UI does not come from a chaotic grid. It comes from what you do within a disciplined structure.
Keep the container simple.
Always. Start your web projects with either a standard 12-column or a 16-column grid. Those 2 frameworks have powered the internet for decades because they offer the absolute best balance of structure and flexibility.
And as you build these simple grids, specifically if you are building responsive grids that change from desktop to tablet to mobile, there is a massive operational practice regarding developer empathy.
Oh yes. Naming conventions.
Naming conventions. Explain why that matters so much.
This cannot be overstated. A design file is not an art piece. It is a set of instructions for an engineer. If you have 3 different grids for different breakpoints, do not leave them named Grid 1, Grid 2, and Grid 3.
That tells the developer nothing.
Nothing. Name them clearly based on their behavior. Desktop fluid 12 cal, mobile fix 4 cal.
If your multiple grids are logically and explicitly named, the developers can map those names directly to CSS variables easily in the code.
It eliminates guesswork, prevents deployment bugs, and stops the endless back and forth Slack messages asking, hey, what spacing am I supposed to use here?
Which perfectly transitions into the ultimate workflow recommendation from the book. This is the exact order of operations that senior architects use to build scalable systems.
And it feels totally counterintuitive when you're staring at a blank canvas, but it is the secret to moving incredibly fast later in the project.
What's the first step?
The order of operations is a process of refined scaling. Step 1. Do not touch the page layout. Get your initial component styles nailed down first.
Before the grid?
Yes. Design your buttons, your input fields, your individual data cards. Establish their internal 8-point spacing and their CAP height alignment.
Get the atomic elements perfect first.
Exactly. Then, step 2. Once you understand the geometric footprint of those atomic components, then you define your macro grid. You build the 12 or 16 column structure specifically to accommodate the physical reality of the components you just built.
Ah, I love that.
Yep.
You don't build a house and then hope the furniture fits. You measure the furniture and build the rooms to hold it perfectly.
Precisely. And finally, step 3, the final adjustment. You place your components into the macro grid, and you perfectly fit that grid. You make the tiny subpixel adjustments required to make them lock into the tracks.
Now, anyone listening to that workflow might feel incredibly frustrated. It feels excruciatingly slow at first.
Oh, it tests your patience.
You want to immediately start painting the whole screen, but this framework forces you to spend hours just measuring the padding inside a single button and calculating column math before you even lay out a landing page. What is the actual payoff for that extreme front-loaded patience?
The payoff is exponential velocity and frictionless deployment. Yes, it feels like hitting the brakes in week 1, but by week 4, when the client asks for 50 new screens, you aren't designing from scratch.
You are simply snapping mathematically perfect Lego blocks onto a mathematically perfect base plate.
You prevent visual chaos, you guarantee unshakable consistency across massive applications, and you hand developers a blueprint that practically codes itself. You minimize developer bugs.
You are trading a few hours of upfront mathematical discipline to save thousands of hours of chaotic revisions and bug fixes in production.
You are building an unshakable foundation instead of building a beautiful house on quicksand.
As we close out this incredibly deep dive into the hidden architecture of the interfaces we touch every single day, I want to leave you with a shift in perspective.
This is a great thought to mull over.
When we talk about rigid frameworks, when we spend all this time talking about mathematical boundaries, forced multiples of 8, locking elements to invisible columns, and restricting line widths to exact human biological limits. It's very easy to view the grid as a cage.
It feels restrictive to a lot of creatives.
It feels like the antithesis of artistic freedom. But I want you to consider the exact opposite. What if the strict, unforgiving mathematics of an 8-point grid is actually the very thing that sets your creativity free?
That's a powerful idea.
Think about the cognitive load you waste agonizing over whether a button should be 12 pixels or 15 pixels to the left. Think about the hours lost nudging a text box up and down trying to make it look right.
It's exhausting.
What if, by allowing the mathematical structure to definitively solve all of those agonizing spatial questions for you, your brain is finally completely unburdened? The geometry is solved, the architecture is sound.
You are free to focus on the art because the structure is already solved.
Exactly. You can focus 100% of your energy on the color theory, the typography, the motion, the user narrative. The grid isn't a cage that restricts your creativity. It is the scaffolding that allows you to build as high as your imagination can reach without the structure collapsing.
When the math handles the logic, the designer is free to handle the emotion.
Absolutely. And the entire blueprint for this mathematical scaffolding we've explored today, every concept, from the fluid equations to the CFP height alignments, is sourced directly from Chapter 08, Layout and Grid, in the book Design User Interface.
It is an absolutely essential resource. If you are serious about transitioning from just drawing pretty screens to engineering actual robust digital products, this framework is mandatory reading.
You need to have this reference on your desk. You can find the exact book right now by going to https://hype4academy.gumroad.com/Lui book.
It'll change how you design forever.
And we have made it completely frictionless for you. You can grab your copy right this second by scanning the QR code of the book link provided right down in the description below.
Get the book, learn the math, master the grid.
And if you want to keep exploring the invisible mechanics of the digital world, if you want more deep technical design breakdowns and career-building content just like this, make sure you hit that follow button.
We're just scratching the surface of what makes software truly great.
Thank you so much for joining us on this deep dive. Now go out there, embrace the constraints, and start building some mathematically flawless interfaces.